Today's topic is Kruskal algorithm. So once again, we are going to consider the greedy technique. We are still in the greedy technique. Uh, One more problem that comes in greedy technique is Kruskal algorithm. Okay, and one more point to share why it comes why the Prim's algorithm comes under greedy technique. What is greedy there? So why the greedy technique comes here? So that is the thing. In Prim's algorithm, what happens in every step? What you do, you choose the minimum edge. So since you are choosing the minimum edge in every step, and you take the problem near to the solution, isn't it? So this problem it comes under minimization problem. It is a minimization problem, and hence since it chooses the least, so it can either choose the greatest value or the least value. Okay, now one more technique is the one more problem is Kruskal algorithm. So as we have seen in the previous class, even this algorithm, it is also used to find the minimum cost spanning tree. So both Prim's and Kruskal algorithm both serves the same purpose. So both are used to find the minimum cost spanning tree. Okay, so keep that in mind. So the person behind this Kruskal algorithm is James Kruskal. So he is the one who discovered this algorithm. It is used to find the minimum spanning tree. See, we use the term minimum spanning tree, or sometimes we use the word minimum cost spanning tree. Both are same. Okay, now third point, the algorithm, how this algorithm constructs. The algorithm constructs a minimum spanning tree as an expanding sequence of subgraphs. Observe this. The algorithm constructs a minimum spanning tree as an expanding sequence of subgraphs. It is not one subgraph, it is multiple subgraphs. Whereas in Prim's algorithm, only one subgraph, it expands until the end of the problem. Until you get the solution, only one subgraph will expand. Okay, whereas in Kruskal algorithm, there may be more than one subgraphs, okay, which are always acyclic. The subgraphs are acyclic, but are not necessarily connected on the intermediate stages of the algorithm. So what it tells is, in the intermediate stages, until you reach the solution, final solution, optimal solution, there may be n number of subgraphs that are expanding, okay, and finally all these subgraphs will get connected to one another and it forms a spanning tree. So that is how the Kruskal algorithm works. So based on this point, later I will show one illustration which by which you can understand the difference between the Prim's and the Kruskal. We'll take a problem. It is the same problem. The same input graph is considered. It contains 6 vertices and some edges are given. Totally 1, 2, 3, 4, 5, 6, 7, 8, 9 edges are there. Okay, and the weights of the edges are same as that of the previous problem. Now, what do we have to do in this problem? First, the first step is we have to take 3 columns as that of the previous problem. We have to take 3 columns. But now here the columns names are a bit different. The first column is 3 edges. It is 3 edges, which are the edges that you consider. Whereas in the Prim's algorithm, you considered the vertices. You considered VT. The vertices was the first column. Here it is edges. 3 edges you have to consider. Second column, sorted list of edges. Now you have to sort the list, sort the edges, and you have to make it as a list. Now, if you look at this, out of all the edges, one BC is the edge which has 1, a cost of 1. Therefore, it comes at first. Next, there is an edge EF which has a cost of 2. That comes next. There is AB which has a cost of 3. That comes next. There is an edge BF which has a cost of 4, which comes next. There is an edge CF. See, there are two edges BF and CF, and why BF has come first? Because B is smaller than C. Okay, so you have to follow this convention also. So here once again AF and DF both are having same cost 5, but AF has to be written first than DF. Okay, like this you have to sort all the edges and you have to write its cost below the edges like this. Now, after doing this, you take the first edge. Why you choose the first edge? Because it is the smallest edge. Since it is the smallest edge, we consider this edge BC to be part of the spanning tree. Okay. Now BC is chosen. If you look at the illustration on the right hand side, BC is chosen, which is having a cost 1, and BC is marked with a dark line. Okay, this is the first step. Now there is one subgraph. One subgraph has been chosen, that is BC. Two vertices BC and the edge BC. Okay. Now one subgraph has been included in the spanning tree, in the growth of the spanning tree, in the process of finding the spanning tree. Now what is the next step? So since we have considered BC, the next step is the first column. In the first column, you have to specify that you have chosen BC to be the edge. To be the edge. What is the first column? First column is tree edges. The first tree edge, spanning tree edge that you are considering is BC. Okay. Next, from the same list, the list doesn't get updated. Its cost remains same. Therefore, just write the edges and the cost that is similar to the previous step. Now underline. In the first step, what you do is either you put a box for BC or you can make an underline. So putting a box is better, I think. So BC is, you put a box for this BC. In the second step, you put a box for EF. So before putting a box for EF, so you first check whether considering EF, whether if you consider EF, it forms a cycle. Okay. So first you have to see the minimum edge. After taking that minimum edge, the next step is you have to check whether it forms a cycle. If I choose this E and F, whether it forms a cycle with B and C, no, it doesn't form a cycle. Therefore, now this can be chosen. You can put a box for this. You can put a box around E and F. So like this. So now, yes. Now EF is chosen. Since EF is chosen, now you make that EF dark line. So telling that it is a newly chosen edge. Now if you look at the diagram, how many subgraphs are there? There are two subgraphs. One is EF, other one is BC. So that is the point that differs this algorithm from the Prim's algorithm. In the Prim's algorithm, it expands as a single graph, whereas in Kruskal algorithm, the spanning trees expands as multiple graphs. This is one graph. EF is one subgraph and BC is one more subgraph. Okay. Now let us move to the next step. Since you have marked this EF, you take that EF to the left hand column, the tree edges column. Now we have included EF to the spanning tree edge. The next step, write the same set of edges and just look at whether AB, whether choosing AB, whether it forms a cycle. If I choose AB, there is no threat that it forms a cycle. It doesn't form any cycle. So that means what? We can consider this AB. So put a mark for that. Put a square mark for that, telling that you have chosen AB to be the next edge. Okay, now AB is chosen as the next edge. Now, you mark that AB in the dark line, and now look at this. Initially, the subgraph was having B and C. Now the subgraph has expanded, and it has the vertex A now, and it includes the edge A, B. Now the subgraph is expanding. This is what the meaning of that definition. The subgraph goes on expanding. Now still there are two subgraphs. This is one EF is one subgraph, ABC is one more subgraph. Okay. Next, take this AB and put it to the left hand column. Take that AB and put it to the left hand column. So that AB3 cost has come to the left hand. Now, once again, write the same sequence of edges. Now consider the edge BF. Now, if you consider BF edge, whether it makes a cycle. Look at the diagram. BF, if we consider BF, it doesn't forms any cycle. It doesn't forms any cycle. Therefore, you can choose this edge BF. So what you do, you just mark that. You just mark that edge BF. Okay, now BF has been added and it is highlighted using the thick line. Dark line is being put. Now, if you observe this step, what has happened here? Now, in the previous step, there were two subgraphs. Now, the two subgraphs, now it has expanded and one subgraph has connected to the other subgraph and it has become a single subgraph now. Okay, now in this step, there is only one subgraph. Okay, so this is how it works. In this example, initially there are only two subgraphs. If the graph size is very large, there may be a chance that there are multiple subgraphs. For example, think that initially, in the initial stages, there will be around five subgraphs. So once those subgraphs keep on expanding, what happens? The total number of subgraphs becomes less because one subgraph will get connected with the other subgraph. And finally, what happens? Finally, in the last step, all the subgraphs gets connected and it becomes a single subgraph, or what we call it as it is a spanning tree. Now come to this last step. We have chosen this edge BF. It is returned to the left hand column. It is included in the left hand column, tree edges. Now, in the previous step, we have chosen BF. Next one is CF. CF, we have to consider CF. Now see whether adding CF or considering CF, it forms a cycle. See, if you look at here, if you add C and F, if you consider C and F, this one forms the cycle. BCF forms a cycle. Therefore, CF should not be considered. You would skip this and move to the next edge. Check whether AF forms a cycle. A and F. If you choose AF, once again it forms a cycle. AB, F, A. So this is a cycle. So reject this also. Move to the next one. It is DF. DF. D and F. If you choose DF, whether it forms a cycle? No, it doesn't form a cycle. Now what you have to do? You have to highlight this. Either underline this or use a box. Put a box around this, telling that you have chosen this. Now DF is chosen. It is highlighted. It is thickened in line, and DF has been included in the left hand side. Okay. Now still there are three vertices. Sorry, three edges are left. Whether we should continue? No, there is the diagram tells that this is the last step. But how we will come to know that it is the last step? So answer is totally how many vertices are there? 1, 2, 3, 4, 5, 6. In the spanning tree, what is the minimum number of edges that are required to connect all the vertices? It is b minus 1. Now total number of vertices minus 1. If there are 6 vertices, then totally 5 edges are enough. Totally 5 edges are enough to make the spanning tree. That means what? You are going to select only 5 edges. So once you choose the 5 edges, you stop that iteration there itself. No, don't continue with A, E, C, D and D, E. I hope this is clear. So finally, what you do is this is the output. Now, if you look at this output, now this one is a single subgraph. Multiple subgraphs have expanded and they have connected themselves, forming a single subgraph, and which is nothing but the spanning tree. And this spanning tree has the minimum cost. Because why this has the minimum cost? Because in every step you have chosen only one. You have chosen the edge which is having the least cost. So since you have chosen the edge which is least cost, this output should have the minimum cost. The total number, you check the total count of this. Okay, and observe whether the output of this is same as that of the previous one, and also check whether the cost remains same. So I hope you have understood. So finally, what you are supposed to write, you have to consider You have to take the edges from the left hand column. Whatever edges that are considered, you have to take them and you have to write in a set format. You have to write ET is equal to BC, comma EF, comma AB, comma BF, comma DF. And you have to write total cost. Total cost of this spanning tree is 3 plus 1, 4. 4 plus 4 is 16. 16 plus 2 is 18. 18 plus 5 is 23. So 23 is the total cost. Now we should solve this. So let us see the algorithm now. It is very simple. You can understand this very easily. Kruskal algorithm. The input for this is a graph. Graph is G. Kruskal algorithm for constructing a minimum spanning tree. What is the input? A weighted connected graph. It should be graph should be connected and it should contain weights. What is the output? The output of this algorithm is ET. You should tell which are the edges that are selected. Okay, the set of edges composing the minimum spanning tree of G. Now, what is the first step? First step is sort E in non-decreasing order of the edge weights. So this is the first step. You have to sort the edges in ascending order and you have to write its cost below the edges. ET, the edge set, initially it will be empty, it will be null because you have not chosen any edge. So stepwise, iteration after iteration, the edges will be added to this edge set ET. You take one variable called as E counter, initialized to 0. You take one variable called as K, that is initialized to 0. While E counter is less than B minus 1, while E counter is less than B minus 1, do. You take, you increment the value of K. That why this volume is there? It executes for number of vertex minus 1. If there are 6 vertices, it executes for 5 times. So that is the meaning of that. Okay. Now, if the condition. Now, what you're supposed to do is you have to take one of the edge, the minimum edge, the first, whichever comes first from that list of edges. You have to take that because it contains the minimum cost. If look at this, if ET union EIK, if ET union EIK is EI1 because K is 1. 1 means it is the first edge. Okay, it is in the series. Why that K is being taken is to give the numbers for this. This is K1, EK1. This is EI1. This is EI2. This is EI3, EI4, edge I5, edge I6. So like this, to give the numbers, this K has been taken. Shall be next. If you consider the first I1, first edge, what it whether if you include this to the edge set ET, whether it forms a cycle. If it forms a cycle, or whether it doesn't form a cycle. What it is, if ET union EIK is acyclic, whether it doesn't form a cycle. If it doesn't form a cycle, it means what? That you can consider that first edge. You can consider the first edge because K is 1 now. Okay. Next, if you have considered that edge, what you are supposed to do? You have to take that edge and you have to add it to the edge set ET. Now ET is updated and ET contains the first edge. Increment the E counter. E counter is equal to E counter plus 1. So now it once again goes to a while loop. Now the E counter is 1. It is lesser than 5. It is lesser than 5. It comes here. K gets incremented. K becomes 2. If K becomes 2, you have to consider the second edge, EF. Okay. Next, if ET, comma U, if you take the second edge, whether it is acyclic, in our example, yes, it is acyclic because you are considering the second edge also. You are considering EF also. Okay. So hence, what happens? Even that second edge is included in the edge set ET. E counter increments. E counter becomes goes here. 3 is less than 6. K is equal to K plus 1. K also K is now, it was initially, yes, it is now 3. K is 3. Now check the third edge, which is that third edge, AB. Yes, AB you are considering AB. And hence, it doesn't form a cycle, and that AB is added to the edge set AT. Increment the A counter. Now the E counter becomes 3. Initially it was 0, 1, 2, 3. It comes here because 3 edges have been included. What is K? K is 4 now. Okay, K has become 4. That means you have to consider the fourth edge. You have to consider the fourth edge. You are considering BF. Yes, you are considering BF, and hence um, that BF is included in the edge set and increment the counter. E counter becomes 4 now. It goes to the while loop once again. It is lesser than 5, and hence K becomes 5 now. K is equal to K plus 1. Now fifth edge. Fifth edge is CF. Fifth edge is CF. We are considering that. So whether it is acyclic, no, it forms a cycle, isn't it? Now what you are supposed to do is you are supposed to it doesn't increment the E counter. It doesn't update this. It will once again go back to the while loop. The E counter remains same. Okay, because you have not considered any edge. What about K? K becomes incremented. K gets incremented. K becomes 6. So sixth edge AF. Even AF we are not considering. So hence it forms a cycle, and then also these two statements doesn't get executed. Once again it goes to the while loop. So once again it is lesser. A counter is lesser than 4 is lesser than 5. So K gets incremented. K becomes 7. Okay, now seventh edge DF. You are considering DF, and hence you are including that DF into the edge set ET, and you are incrementing E counter. E counter becomes 5. 5 lesser than 5 is false. It comes out of the while loop. Finally, edge set ET is returned. So this is how the algorithm works. So this is after 2 steps. So how it looks after 2 steps. This is one subgraph. ABC is one subgraph. This is the expanding subtree number 1, and EF is one more subgraph. This is expanding subtree number 2. And after 2 steps, this is the output of ET. First, I have included AB. Next, sorry, first is BC I have included. Next, I have included EF. Next, I have included AB. So this is the set of edges. So this is how it goes. I hope you understood today's concept of a Kruskal algorithm. Once again, just have a look at this definition. The algorithm constructs a minimum spanning tree as an expanding sequence of subgraphs, not just one subgraph. It is sequence of subgraphs which are always acyclic. It should not contain a cycle, but are not necessarily connected. In the initial stages, they are not connected, but later they get connected and they give the final output. In the intermediate stages, they will not get connected. All the subgraphs are not connected, but as the stages increases, as the iteration grows, some of the subgraphs get connected to one another, and finally it becomes a single spanning tree.